Do you mean the 5th of the 11th?
Hello and welcome back to Calculus 1, section 4.1 on min and max problems, also called the extrema. We are going to use calculus to determine the extreme points of a function. So when you look at the function, let's say something that would look maybe like that. You can put that in XY coordinate system. We don't care about it now. We see that there is a max over here. There is a minimum over here. There is another max over there. What's unique for all 3 points is what we call horizontal tangency. All of these points have a horizontal tangent line like that, and the slope is always 0 for all of these. From this, we conclude that we can find min or a max of a function by setting f prime of x to 0. This is not the end of the story, but it's something that will be used 95% of the time, 99% of the time, whatever. So we see that whether we have a minimum or a maximum, it doesn't matter. It always has a horizontal tangent line. Horizontal lines have a slope of 0, and we talked about it 2 classes ago when we talked about a tangent line. We said that tangent lines, m is equal to the derivative computed at a point. So we can actually compute dx. We can find min and max of f of x by working out the location. Yes?
What if you have a line that just ends? Would that not be on the derivative? Would it be an open hole?
Very good question. That is going to be, yes, that is going to be in the second part of this lecture, where we are going to see it as a min or a max, because it will have a point that ends. If you leave it as, in this case, as the, really? If you leave it like this, where it goes forever, then it doesn't count, because it will go to infinity. But if it actually ends abruptly, like a square root of x, that's what you're talking about. Square root of x abruptly starts at 0, 0 and goes like this. That would be a minimum, yes. So, but that's the second part of the same lecture, so we'll come back to that. Now, before we get there, let's first talk about 2 different types of min and max that you can get. We see that these 2 max values are not the same, right? One is higher than the other. So the higher max value would be called an absolute max. And the lower one would either be called relative or local. So I can go here and I will call this one absolute max, and this one relative max. We can also call it local max, or local max. So whether you use absolute, there is also global. That's also depending on which book. So that's going to be also global max. So absolute or global, or relative or local. So those are the words. I don't care which one you use. Now, why is this one absolute? It's absolute max because it is the highest y value on the entire function. Highest y value of the entire function, and that's why it's absolute max. If you have multiple highest points, all of them would be absolute max. They are not demoted down to relative. So sine x sine x has infinitely many max values, absolute max values, and infinitely many absolute min values, because they're all at once and negative ones, and you have infinitely many of them. So sines and cosines would have infinitely many of those, but then if you just have, let's say, x squared, the U-shaped one, the parabola, that only has absolute min. So this one is absolute max because its y value is the highest y value that the entire function has. This one is relative max. It's a maximum in its neighborhood, okay? When you take a look at some neighborhood around this point, it's a maximum in that neighborhood. So you can think about this as, I don't know, President of the United States and the governor of a state, or you can think of the governor and the mayor of a town, whatever, I don't know. So, you know, there are these ranks that are most important in the smaller, right, sample, but for the population, absolute is the highest, or the lowest if it's a minimum. Now, what do you think about the minimum point in this particular case? That minimum point, is that absolute minimum or relative minimum?
Relative.
Why is it relative minimum?
Because the ends go below which?
Very good. It is a relative minimum because all of the values, come on, there we go. All of the values here and here have smaller y values than the minimum, which is why it is not absolute. So this one over here would be relative minimum because it is not the lowest point. Now, do we have functions with the absolute minimum? Sure. You just draw x squared, right? X squared graph would have ABS min. That's the name of the game, right? So now we understand absolute versus relative. You can also use global and local if you want to. So now that we understand the types, all of them are found the same way. So min, max points are called extrema. Extrema. Extrema occur at what we call critical point. And now we are going to write the definition for the critical point. I will follow the same wording as in the book. So, definition, critical point. Here we go. An interior point C of the domain of f of x at which number one, f prime of c is 0, or number two, f prime of c does not exist, is called the critical point of f of x. Critical point can be found in two ways. One way, take the derivative of the function, set it equal to 0, and compute the location of the critical point. That critical point will be min or a max. Or if the derivative doesn't exist at some location, that also becomes a critical point. Now, guys, you have to be careful with that second one because you can also run into a vertical asymptote with a second one, and that's not going to be a critical point because vertical asymptote cannot have any points on it, so clearly can't have min or max. So let's outline the examples for all of these and then use them in some interesting problems. So say you want to first do the cheapest problem, f of x equals x squared. All right, that's it. So what do we have here? Well, we already know the answer, right? We are looking for a critical point and we're going to get the minimum at 0, right? But we already know the answer, but let's compute it. Really?
Or not.
Let's compute it or not? Why? Why? Come on. Take the derivative, set it equal to 0, and solve the equation until I figure out what. I swapped the computer for these reasons and I'm still getting the same issues. Just gonna wait for a second then. Around. Anyway, so we take f prime of x, which is 2x, and we set it equal to 0 because we want to force horizontal tangency. When you solve the equation over here, you will get x equal to 0, and that one is your, what we would call, critical number first, because it's just the x coordinate. You will find the y as f of 0, which is 0 squared, which is 0, and then you get your 0, 0, which is critical point. See, point has two coordinates, x, y, or three coordinates, x, y, z for Calc 3. If you just get x equals 0, that's a number on x-axis, so we call it critical number. You are not going to be marked off if you call it critical point, because it is a one-dimensional point, but, you know, critical number for a single coordinate, and then critical point when you have the full 2D or a 3D, which would make sense. And now, we just know it's a minimum because we know what the graph looks like. Now, there are certain cases when you don't know and you have to compute. We'll cross that bridge when we get there. So, critical point, which will be absolute min, because, right, it graphs this way and it's absolute minimum. So, we're all good here, right? We all know what's going on with this problem. So what we did is we took the derivative and we understood that this particular derivative here exists for all values, which is why we don't have to consider the second part. And so it exists for all values, so we just set it equal to 0 and we calculated where the value is. Great. But now you can have a problem that goes like this. F of x is given as absolute value of x. And what's happening now? Well, you recall that the definition for absolute value of x is x and negative x. So x for all values larger than 0, and negative x for all values smaller than 0. So you can represent your absolute value function as this not the step function, sorry, the piecewise, thank you, function. Good. Now, what was the derivative of this function? Well, if you take a look at this derivative, you see that the derivative of x is 1 for all x's larger than 0, and derivative of negative x is negative 1 for all x's smaller than 0. So your function which was the V-shaped, right, function like that. That's your absolute x graph. Produces the derivative which has -1 coming in and +1 going out of x. So what we see is that derivative does not exist at x equals 0. The limit doesn't work. You are right. I can, even if I put the point here, the derivative does not exist because the derivative is the limit, and the limit needs to approach from both sides. But when you approach from the left, it gives you -1. When you approach from the right, it gives you 1. So the derivative doesn't exist. And you are going to learn as a rule in mathematics, anytime you have a spike or a cusp is when it goes like that, right? Anytime when you have a spike or a cusp, or you have a function that goes vertical for some time and goes like this, there is no derivative there. Derivative does not exist at that value. So we would see that this problem has absolute minimum at x equals 0, which is right at the origin. So absolute minimum at x equals 0, or you can say at 0, 0, right? Again, and that's the answer. So if you end up having an issue with the derivative, your min and max can hide there. Now we are going to take a look at f of x equal e to the x function. What's the derivative of e to the x? Very good. And when I set that equal to 0, what do I get?
It doesn't exist.
Doesn't exist. Very good.
You can't do square root. No, log of 0 doesn't exist.
Log of 0 is negative infinity, right? So now we have exponential equation to solve e to the x equals 0. Last class we talked about logs, so you can convert this into ln of 0 equals to x, right? And this over here does not exist. Another way you can solve this, which is a much better way, is to graph it and realize that your e to the x never crosses x-axis. So it has no solution. Now I need to talk more about that. But before I talk more about graphical solution, we are understanding that there is no solution. And because there is no solution, it means no critical point, which implies no min-max. So here is the example that has no minimum and no maximum at all. Now there are many functions that have no min or max. Another example of this would be obviously 1 over x. It has no min, it has no max. So you can try and work out 1 over x. So another example with no min max is f of x, 1 over x, and I invite you to obviously try that on your own time. Now, before we go on, I will just remind you guys that not all equations can be solved using the algebra. For instance, if you mix two worlds that are not compatible, you can't solve the equation. I'll give you an example of, let's say you have e to the 2x minus 1 is equal to x plus 3. Let's say this is the equation that you are looking at. This is not cool, because on the left-hand side, you have exponential function. We call that transcendental. On the right side, you have linear function, and they are not compatible with algebra, with one another. There is no way, comma, in hell, comma, to solve this algebraically. You can move 1, you will get e to the 2x equals x plus 3. X plus 4. And then you would say, yeah, just do the log, and that will free up 2x. Okay, sure. I'll put the log on both sides. So I put ln over here, and I put ln over here. And what happens? Log will kill the e. So now you have 2x equals ln of x plus 4. So I freed x on the left, and I buried the x on the right. There's no way to solve this. So now, what are you going to do? Remove ln by using e on both sides? Right? You have, yeah. So you have the idea. So the problem like this cannot be solved algebraically. So how do we solve it? Well, we solve it with either numerical methods. We are going to learn something cool called Newton's method to find zeros of the function, which uses calculus. Or you can solve it graphically. In the end, graphical solutions are always there for you. Look, if I graph these two equations and they intersect, their intersection points are the solutions of the equation. So I have my x plus 3, which is a 45-degree line, x plus 3, and then I have e to the 2x minus 1. So e to the 2x minus 1 is going to look like this. I see that there are two solutions that we can numerically find, and depending on how good your sketch is, you would know where to look for them using numerical methods. Okay? And then in Calc 2, you're even going to get better tools. Now, does this numerical method work 100% of the time? The answer is yes. So let's take a look at this terrifying equation, x plus 2 equals to 5. How do we solve this equation? Well, all of you want to do the same thing. Subtract 2 on both sides and be done, right? So minus 2, x equals 3, and you walk away. Well, let's solve this equation graphically because it's better. So what am I going to do here? I'm going to graph two functions. I have x plus 2, which is a linear line. So x plus 2 is a 45-degree line going through the y-intercept 2. On the right-hand side, I have a constant function 5. So 3, 4, 5. Where do they intersect? Magic. They intersect at x equals 3, right? I know, magic. 100% of the equations can be solved graphically. Depending on how precise you are when you draw these functions, you will be able to read the answers off of those functions. So the solution to every equation you ever see in any course, including all of your engineering and physics and everything else, solutions are always when the equation on the left and equation on the right intersect on the graph. The x-coordinate of that intersection is going to be the solution for that equation. So this point over here is 3, 5, and from there I extract that x equals 3 is a solution. It's a very simple idea. So now with that out of the way, and being safe and secure that you can always solve the equation even though when algebra fails, right? We can now go and dig in and work on a whole bunch of problems that have polynomials and exponentials and logs and a whole bunch of stuff. So here is a problem that old edition of the textbook would like you to try. F of x is equal to x over x squared plus 1. You don't know what the graph is. You don't care what the graph is. Take the derivative, set it equal to 0, and get the equation. Get the critical point.
No. You would have to multiply x squared plus 1 to both sides.
Yeah.
So you have x squared plus 1 times y. What was your final?
The point on the
Yes.
1, 0.
1, 0, that's the point you got? But yeah, this is your x right here, yeah, so.
Oh no, it's y, so it's 0, 1. I think I'm
No, you're right. No, you're right. Because you
I
said
am.
x is 0. So that makes sense 0, 1. Okay. That would be the critical point. And if not,
Is it 0, 1, or am I just confusing myself?
Wow, let's see.
let's see.
Let's see. First off, I'm going to take a look at this and see that there are no vertical asymptotes because the denominator can never be 0, which is awesome, right? So we can start there. Now, we find the derivative. By the way, no vertical asymptotes means that the does not exist part most likely will not kick in, which is the part 2. All right, so what's the derivative here? We have x squared plus 1 squared, x squared plus 1 times 1 minus x times 2x, right? Simplifies into x squared plus 1 minus 2x squared divided by x squared plus 1 squared. Simplifies into, let's go f prime of x, is equal to 1 minus x squared divided by x squared plus 1 squared. And now we set this equal to 0. When you have something like this equal to 0, what's the part you don't care about? Denominator, because when you cross multiply, denominator will multiply into a 0 and just go away. So the only part that we have to consider is 1 minus x squared equal to 0. Now, hopefully you factor this one into 1 minus x, 1 plus x, and you have your x equals 1 and x equals negative 1. Right? So now you will find y values for each one of these and have your critical points, which are either a minimum or a maximum. So we are going to first calculate f of 1. So you take original problem and plug in 1. So that's going to be this, which is a half. So we have one critical point to be 1 half. Then we calculate the second. Guys, note there are no derivatives there. We are calculating the y value. For y, you're using original problem. For slopes, you're using the derivative. So over here we have negative 1 divided by negative 1 squared plus 1, which is negative 1 half. So now we have negative 1 half. So these are critical points. Critical points. Are we cool? Now you might ask, well, which one is the min, which one is the max? Are they both max? Are they both min? Like, what's going on? Yes, do you have an idea of how to tell?
I'm assuming the negative would be the mins and the positive would be the max.
Now, let's say you have a function that looks like this. Oh, sorry, I drew this wrong. You put a slant asymptote, like this, and here is your minimum on the positive and the maximum on the negative. Completely opposite. Okay, so the way to tell is going to come up in one of our next lectures. The only thing that you can do today is to actually do the annoying calculation to figure out. Now let me show you what I mean by annoying calculation. You know that you have a point that it's at, if this is 1 and this is 1, you know that there is a point at 1 half. Now you don't know if it's a min or a max. What you can do is you can compute the function at, let's say, a half and 3 halves. Those 2 points will provide you with y values that will be higher or lower than the y value you have, creating minimum or a maximum, right? So it's annoying because you have to compute these 2 points.
Can you just do 1? Can you just do 1?
No, because there is also something that it's called an inflection point that does this. In which case 1 is below, 1 is above. We did not talk about inflection points, so your question is valid, but no. Hey, did you phone?
Yes.
Okay, your phone is with security.
Okay, thank you.
So yeah, we called the security. They picked it up.
Okay, thank you.
So you have to go yeah, you have to go to the Somerset building. Somerset building security.
Okay, thank you.
You're welcome.
Yes, take care, sir.
So we have minimum, maximum, and something like this is called the inflection point, and it will have 1 lower and 1 upper. But we are not there yet, so I'm not talking about it. So your question is valid, but no. So right now you have to compute 2 points. So what I'm going to do is to test 1/2. I'm going to compute, I'm going to compute the y value at no coughing 1/2, and that's going to be 1/2 divided by 1/2 squared plus 1. And we are going to get a number here. So that's going to be 1/2 divided by 5/4. And then these guys will cancel, so 2/5, right? And now 2/5, and then we compute f at 3/2, which will give us 3/2, and then 3/2 squared plus 1. And this is going to be 3/2 divided by, that's 9/4, 13/4, right? 13/4. And when we cancel these two, yeah, but we're canceling 2 and 4, so it's 6/13. So both of these are smaller than 1/2, right? So 2/5 is smaller than 1/2, 6/13 is smaller than 1/2, and 1/2 is the y value. So you have a situation where at 1/2 you have a number that is smaller than at 1, and another number that is smaller than 3/2. So this point is a max, because it would create a situation like this. So we have max at 1/2. So it's really annoying now, because you have to compute additional points. You can't tell. We are going to have, it's either next section or the following section. So Thursday, we are going to have a method that will do this way, so you don't have to compute and mess with any of these points. So a little bit annoying now, but such is life. One more example, and then we're going to do the second part when we get to do one more thing. So let's see something that you guys are going to love. Oh, this is cool. Really? Like, I find the coolest problem ever, and then it's just
Too cool for you.
projector didn't die. What's wrong now? There we go. Take the derivative, set it equal to 0, solve it. keeps cutting out. What type of the derivative?
Chain.
Great. So we are going to do logarithmic differentiation very quick. So the way this works is we copy the problem as is, and then just follow with the log part, which is going to be 2 over x plus 1 over 2x plus 1, obviously. Very, very quick.
Sorry, I forgot to do that. Can you just like reteach me how to do that? That whole like log thing.
No, you can just do the product rule. It's fine. Yeah, sure.
Oh, come on.
So obviously the derivative is this because, you need a factored form. So it's just quick, right? And now you have 3 factors. You set each one of these to 0, which will give you values that you will consider. So there is x squared equal to 0. There is a square root of x plus 1 equal to 0. And then there is 2x plus 1 over 2x plus 1 equal to 0. So 3 separate equations to solve. The first one is x equal to 0. Easy peasy, right? The second one is x equals negative 1. Easy peasy, right? And now the third one, the third one is easy peasy too, because you set this as 2 over x equal to negative 1 over 2x plus 2. And now you cross multiply into 4x plus 4 equal to negative x. Move x to the other side, you get 5x equals to negative 4, and x equals to negative 4/5.
I didn't get it.
Yeah, it's just quick. So when you end up with a 2-term like this, you send this one to the other side, and then you just do cross multiply, and then you solve basic algebra 1 equation. So now we have negative 4/5 as one of the critical points. X equals 0, x equals negative 1. And if you care about the y values, you plug them back in original problem, and you compute their y values, right? So you will have to compute f of 0, which would be 0 squared times square root of 0 plus 1, which is 0, which gives you 0, 0 point. Then you will have f of negative 1, which would give you negative 1 squared times the square root of negative 1 plus 1, which is also 0. And finally, f of negative 4/5, which is negative 4/5 squared times the square root of negative 4/5 plus 1. Now, negative 4/5 squared, that's 16 over 25, times the square root of 1/5, which is 16 over 25 root 5. Then you rationalize to kill root 5. You get 16 root 5 over 125. And that gives you negative 4/5 and 16 root 5 over 125. There we go. There are 3 critical points, and then we will learn the rest on how to do this. Woohoo! Right? Let's see what else is cool. Can we find something else that it's awesome? Maybe you can come up with something that it's awesome. What would you wonder about? How about something nice? Okay, you want to 4? Sure, I'll accommodate. So cosine to the 4th power of, let's say, 3x. I mean, I don't want to disappoint. I was already set to do some trig, and then he mentioned the fourth powers.
If you were to use the product rule, this would become three different factors, right? Because it would be cosine x, 3x.
No, we're using chain rule, not the product rule, for the derivative. Dang, this was a good exam question. I wasted.
You can sleep within itself. Seasonal.
Change the power to 24.
Yeah.
Okay. Let's take a look. This was awesome.
You're welcome.
Yeah. So now we're going to do some trig. Lock the doors. The derivative will use chain rule, and we are going to use the nested, right? Because we have three functions. We have 3x inside the cosine, and everything is inside the x to the fourth. So the derivative f prime over here is going to be 4 cosine cube of 3x times the derivative of cosine is negative sine of 3x, and all of that is times 3, which is the derivative of the inside. So now everything simplifies into f prime is equal to negative 12 sine 3x cosine cubed 3x. Now at this point, you can go and set both of these to 0 and solve, but there is one cooler thing that you can actually do to reduce the cosine to the 3 to the cosine square. It doesn't matter, but it's just to flex a little bit. So what you can do is you can steal 2 sine 3x cosine 3x, put that on a pile, and then multiply by the leftover of negative 6 cosine square of 3x. Now, why did I steal this? Because this is identity, and it simplifies into sine of 6x. It's a double formula, right? The sine of 2x is 2 sine cosine, but because these are already 3x, the double is 6x. So it simplifies into that, and that's times negative 6 cosine squared of 3x dx. Not dx, it's just 3x. So now when we set this equal to 0,
Disconnected again. I have no imagination.
sine of 6x is equal to 0. They want me to troubleshoot the problem. I troubleshooted it. It doesn't work. And then we have the negative 6 cosine squared of 3x equal to 0. So now, when is a sine 0? When 6x is equal to 0 and when 6x is equal to pi. So that's where you have, right, when you have a sine wave like this.
It's an identity. 2 sine x cosine x is sine 2x. And since there's 3x,
What's that again?
it's 2 sine x cosine x equals sine 2x. Right? Am I right on that?
Yes, I just wrote it in orange. So now if I am solving equation sine of something equal to 0, that happens at the origin and happens here. It does happen at the end, but that's the periodic, right? Like for the origin, so you don't have to repeat it. You already have the 2. So 6x equal to 0 and 6x equals to pi. So 6x will give me x equals 0. And this one would give me x equals pi over 6. Now, I never gave you the interval, so this is infinite. And if we have a solution at every pi over 6, the overall solution is n pi over 6, where this n is 0, plus minus 1, plus minus 2, plus minus 3, ... going on forever. So that's that. On the other side with the cosine, well, negative 6 divided into 0 just goes away. Square root of 0 still goes away. So this is just cosine of 3x equal to 0. And if you consider the cosine, which starts at 1, dips down, goes up, back to 1, it goes through 0 at pi over 2 and 3 pi over 2. So 3x is pi over 2, and 3x is 3 pi over 2 in the solution. And now if you take a look at this, when you multiply, well, when you divide both sides by 3, you get x equals pi over 6. Hey, that's a repeat, right? And on the other side, you divide both sides by 3, or actually you can just cancel the 3's, whatever. Yeah, you will get 3 pi over 6. You know what? I don't want to cancel. I'm just going to leave it like this because you can see it's also in 6's. So all of these are repeats of that. So this is the solution. We have infinitely many min and max values. Know that this function will go on oscillating so the entire section, I mean, there are still logarithmic equations, there are polynomial equations, there's a whole bunch of these kind of things. We did few examples. Good. Now for the second part, guys, we can also have these on the closed interval. And if you have them on the closed interval, the only thing that you have to do in addition to this calculation, is to compute y values at the endpoints, which is what your question was earlier, right? So let's say that I want to check. So now let's say we have finite interval a to b. So find min max on 0 to 6 for f of x equals square root of, let's say, x plus 3. No coffee. So now, what do? Well, we do the same calculation as before. F prime of x is equal to derivative of this, which is 1 over 2 root x plus 3. When you set this equal to 0, and you cross multiply, you get 1 is equal to 0. No solution, which means no critical points, which means no min max. But hold on, this is on the interval. If it's on the interval, we must check endpoints because of AB. So now I don't have any minimum or a maximum for inside the function, but the endpoints are going to provide me with the min max. So from here I will go and calculate y, which is f of 0, and that is going to be square root of 0 plus 3, which is root 3, providing me with the point 0 root 3. Y equals f of 6 is the square root of 6 plus 3, which is the square root of 9, which is 3, providing me with the point 6, 3. When I have these points, let's go like this. Largest y value is ABS max lowest y value is ABS min. Now it works because it's on the finite interval. So now it works. So what I found looking at my problems is that 0 root 3 is the ABS min, and what else? 6.3 is the ABS max. They happen at midpoints. Do they have to occur at midpoints? No. No. Right? I can have other configurations. So you have to, every problem is different. You cannot memorize anything other than procedure. So if I take out of x squared piece like this, so this is part of x squared, say from -6 to 2. Let's say that's the interval. So this one over here is -6, and this one over here is 2. We see that we have ABX max at x equals -6, and ABS, why do I say ABX over there? ABS min at whatever the vertex is. Right? So you do not have to have absolute min or absolute max on the endpoints. You don't, right? They can be both on the endpoints. One of them could be on endpoint, or none of them might be on endpoints, because I can make something that looks like this. None of the absolute min or max are at the endpoints. But you have to check endpoints because they could be absolute min or absolute max. Depends on the problem you have. So now we are breaking our problems into two categories. One category of problems, which is the first half of the lecture, which is going to check infinitely many points everywhere inside the domain. And then the second category of the problems retains everything from the first category and adds an extra step, because when you have the domain, restricted domain, right, you check those endpoints as well, because the problem can end up having absolute min and absolute max. So I'm just going to say ABS min max not at endpoints. There we go. So the entire section depends on your ability to take the derivative using appropriate technique. Obviously, I was, making a joke over there. You could have done that problem using the product rule. Now you would have to factor, obviously. So this problem here, if you use the product rule combined with the chain for absolute x plus 1, right, you would have to run an additional step to factor everything and then put those factors. You have to get the same answers. It's just, it will be a different solution. Now, so what I used was logarithmic differentiation from last class, or not last class, from Tuesday, I believe, last week. So I used logarithmic differentiation, but the product rule would work as well, right? And so you use appropriate technique. Over here, we could have set this equal to 0 and got the same answers. I decided to use some of the trig identities to refresh those and show you the other way of doing it. But you could have set that part equal to 0, and you would have the sine 3x equal to 0, where most of the answers would come out of the cosine in that case. So there will be more work next. There will be more work next class. I am going to. So we are done. We are done for tonight, and I will see you guys on when? Thursday. 2 days. If you're interested in that talk, I'll see you at 1. So in the conference center, and then class is at 6.